All right, welcome to mini lesson 19. We're going to do the theory of Bose-Einstein condensation today. This is the last lecture or mini lesson from chapter 7 of Schroeder. We're still in section 7.6. So the theory for this part is, I think it's pretty difficult, even convoluted. I want to try to work through it with you and emphasize what I think are the most important parts. Given that we're doing essentially an online class with take-home exams, you can sort of imagine if I would give you a problem about this, even if I said just reproduce this derivation, that would be sort of trivial copying for you. So the question of do you have to know this is not really relevant. What's more important is sort of what are the takeaway messages where I might build a more interesting problem that's not just copying. We'll try to do that. Let's see now. So we'll just start with this intuitive review that we've looked at now several times. This is the same slide from last time, where we just point out this observation that we made about the Bose-Einstein occupation function, that if you plot this function for fixed chemical potential at different values of temperature appearing in the factor beta, you see that there's a pileup of occupation at lower and lower energies, closer and closer to the chemical potential. So in this case, I made a chemical potential at 7 electron volts. And as we lower the temperature from red to green to blue, you push all the occupation towards lower and lower energies. So on the blue curve, again, just sort of because of plotting, you don't really even see any occupation because I made the step size small enough that you don't get close enough to the asymptote to actually see it. So, and so this is a weird divergence, right? And it suggests this interesting possibility of a condensation in the absence of interparticle interactions. Very unusual. But I do want to say this is just intuition. This calculation doesn't really correspond to something that is physical. And this is where the discussion of this topic starts to get a little bit subtle. So it's easy to see why it's not physical, because what we've basically done is say that, okay, we've got a chemical potential mu, and we basically said it was fixed as we vary the temperature of the reservoir to which this gas is coupled. Right? And that's not necessarily the truth. You have to be a little bit more careful about how you understand the behavior of the chemical potential with temperature. So this, just plotting the function for fixed chemical potential that's the same at every temperature, it gives you an intuition that there's a strange pileup, but it is not an actual calculation of the process itself. So hopefully it may take a few minutes to think through what I'm trying to say here, but this is not a calculation. It's sort of a hint that something weird is going on. So we actually have to be a lot more careful in how we do the calculation, and it may even feel a little bit hand-wavy, because what we're really doing is we're trying to take fairly difficult math and sort of install physics that we're interested in. We're going to try to come in and say, well, what does it mean to have a phase transition, and how can we manipulate the formulas to understand that physically? But it's not just going to fall out from the math by doing algebra. That would probably be pretty boring. Okay. So yeah, intuition is present but not sufficient. So let's see what we're going to do. The first thing let's do is let's just think about the behavior of the chemical potential at very, very low temperatures, really approaching zero. And so we claim, based on that intuition, that the occupation of the ground state, which let's just say it has energy E0, should be large. Right? So that's not unreasonable, right? We're saying we think there's a pileup. And so let's imagine that N0, the occupation of the ground state, which is the Bose-Einstein occupation function evaluated at E0 at some t and some mu, where t is considered to be quite small, has to be a big number, right? And so if this expression is a big number, it means the denominator has to be small, all right? And so that means that the exponential factor appearing in the denominator needs to be close to 1, right? So again, if you just substituted in 1 here, you wouldn't really be wrong, but you would have done no work. That just says it blows up, and we already sort of knew that from our intuition. What we would rather do is get a function that tells us sort of how things are blowing up and how they're behaving in this limit. So what we should do is expand this exponential to low order in a Taylor expansion. So e to the x is approximately 1 plus x, where x is going to be this factor E0 minus mu over kBt. And so when we substitute that in to the denominator, the 1 cancels with the minus 1, and we're just left with this factor E0 minus mu over kBt. And that gives us an expression that says at very, very low temperatures, the occupation of the ground state is kBt over E0 minus mu. And so from this, we can actually solve for the low temperature dependence of the chemical potential. So the chemical potential is approximately equal to the ground state energy, but then the difference is kBt over N0. So let's keep in mind, N0 might be a really big number, right? It might be a mole, which is huge. So this could potentially be a really small correction. Obviously, as T goes to 0, the chemical potential approaches E0. And indeed, it approaches it from below. So the chemical potential starts at a low number. Ground state energy is here. And as the temperature lowers, the chemical potential moves toward E0 from below. So we have sort of an intuition about the temperature-dependent behavior of the chemical potential. And it's important, right? Because it does show that it's not just a fixed number that you can plug in at every single temperature. All right. So now let's go on to actually think about the supposed phase transition of Bose-Einstein condensation. So the basic idea is that as temperature lowers, we do get this pileup of bosons in the ground state. And so let's say we have n bosons, and let's say they have 0 spin. I mean, if they had any other integer spin, you would just get factors of 2s plus 1 degeneracy under this integral. But we're basically going to use the statistical mechanics approach that we've been using all throughout Chapter 7, which is that basically when we want to calculate an average quantity, we do an integral over something, in this case just 1, times the density of states times the thermal occupation function. So we do this for bosons, we do it for the fermions, we did it for the photon gas, we can do it for the phonon gas. So the number of bosons, n, is equal to the sum of whether there's a state, whether the state is thermally occupied, summed over all the possible energies from 0 to infinity. All right. The density of states here is the exact same density of states that we used for the degenerate Fermi gas, except instead of having a spin degeneracy of 2, it's got a spin degeneracy of 1 because the spin is 0, right? So there's just 1. All right, where are we? And so the expression that you get when you divide that out by 2 is this. And so for a few slides anyway, I'm going to just write this as G0 times the volume times the square root of energy. Kind of the important point here is that we have a square root of energy rather than an E squared like we did for the photons or the bosons. So that's just comes from the fact that you have an ideal gas with a non-relativistic kinetic energy. Anytime you have that, you will get this dependence. Right. So here's the big theory idea, and really the start of where I want you to take something away from this discussion other than just can you copy down the math by looking at these slides. So the big idea is that if you have a phase transition, doing this integral as one piece is extremely dangerous. Something is diverging, namely the Bose-Einstein occupation function may be diverging or misbehaving or whatever. If you have a phase transition, you don't know what a priori. And so what we need to do is tread really carefully with how we treat this integral. And so rather than just treating the number of bosons as one integral over everything, we're going to break it into a piece that we think we can work with and a piece that we think is dangerous, okay? So we're going to conceptually say that the total number of bosons is the number in the ground state, which is the dangerous piece, the piece that should prevent us from just doing this integral straight up. And then a number of bosons that are in excited states, higher than the ground state. And that's a piece where there's no danger, where you could just do the integral, okay? So this is a really key physics, sort of physics input, right? Where you, when you have a phase transition, sometimes you need to break off the dangerous and the non-dangerous pieces. All right. So we're going to be explicit about treating the ground state and the excited state as different parts. And what we're basically going to do is we're just going to say n0 is something. And it may be a really big number, fine. It may be all of the bosons. And then the excited state piece is just this integral. So now I wrote out the integral explicitly. This is very similar to the Fermi integral that we worked with in the Sommerfeld expansion. Only the issue is it has a -1 in the denominator, and that, you know, that is potentially dangerous. And that's the reason we have to do this break-off thing. And it's also a reason why actually carrying out this integral is maybe even a little more difficult than the Sommerfeld. Though probably not. They're probably equally difficult. All right. So note here, I still started the integral at 0 because at that particular low energy, it makes no difference because the density of states is 0 anyway. So you don't really have to worry about where you start the integral when you're dealing with this kind of continuum approximation, and where we've sort of by construction broken off anything that might be divergent. So we're basically saying that the number of excited states is just equal to this integral. We still can't do the integral because we have mu in the bottom, right? And that's a function of temperature. And we really don't precisely know what it is. We know a low order expansion at low temperature. But so we can't do much. Remember, when we worked with a degenerate Fermi gas, we came down here and we did a Sommerfeld expansion. But the reason that worked is because the special shape of the Fermi function, the step function, lets you make some really useful approximations, namely that the derivative of the Fermi function is a super sharp peak. Right? And that is not true here, and we can't apply the same mathematical methods. That's really what this is. These are math methods for dealing with these nasty, nasty integrals. All right, so in fact, what we're going to do is be a little bit crude. And we're actually going to say that within this integral, not generally and not for every circumstance, but at least within this integral that represents the excited states of the Bose gas, we're going to let the chemical potential be approximately 0. And so there are ways that you can make this more mathematically rigorous and maybe even a little bit physically clear that I kind of don't want to do right now, or we're not going to do it at all in this class. Basically, you would sort of make some arguments in terms of a fugacity parameter that we talked about many lessons ago when we introduced grand canonical. But if you're sort of concerned about this, I'm going to suggest that you would go back 2 slides and take a look at, you know, values of the chemical potential that you might get for typical choices of numbers in this expansion. And if you go in and start to think about, okay, let me substitute some typical values of mu, the differences in the value of the integral that you would get compared to some value that's not 0 and 0 are going to be quite small. So again, within this integral, this approximation is quite good. we are not saying that mu always equals 0 for Bose-Einstein condensation. That is not true and would lead to some ridiculous paradoxes. In particular, if mu always equals 0, you can create particles at will only determined by the temperature of your gas. And for real atomic gases, that is not physical. Right? So it's important to understand that this approximation that we're making here applies only to this integral, and is definitely an approximation and is not true for the whole gas. Well, let's just do it. We substitute it in, and now we actually have an integral that we can do. We do our standard thing of letting x equals e over kBt, so that we get an expression that looks like this, where now I've written out the G0 and included the substitution effect of e over kBt, so that we get this funny expression that should sort of look similar to something you've seen before. But then we have an integral over x from 0 to infinity, and so you can imagine just plugging this integral into Wolfram alpha. In any case, it's a known integral. Its value is 2.612. It's related to a Riemann zeta function. I think it's evaluated at 3/2 or something. That's a number that we talked about in the last slides, somehow related to the density of Bose-Einstein condensates from the Anderson and others paper. So if you just plug it all in, you get that the number of excited states is 2.612 times the volume of the gas times 2 pi m kBt over h squared, all raised to the 3/2 power. So this is cool. It's basically telling you, right, as you raise the temperature, the number of bosons in high energy excited states is growing. It's growing as the 3/2 power of temperature, right? Alternately, you can say that as you lower the temperature, the number of excited states is dropping with the same power of temperature. And so if that's dropping, it means that the number of bosons in the ground state has to be growing, okay? And so we need to put in a little bit more of this physics to build up a picture that actually says what we mean by phase transition. And so what we're going to put in to build the idea of a phase transition is that there is a critical temperature. Let's call it T sub c. And so if the temperature is above T sub c, we basically have a normal ideal Bose gas. We can approximate the number of bosons in the ground state as basically 0. What we're saying is there's a negligible fraction in the ground state, and most of the atoms are in excited states. At the critical temperature, we still maintain this condition that the number in the ground states is 0, but as soon as we go a bit below the critical temperature, we form a ground state condensate, where the number of atoms in the ground state is equal to the total number minus the excited state, and n sub 0 in this case does not equal 0. Right? So this is physics right here. A lot of what we did in these other slides is a little bit of math and approximations and stuff like that. But this is where we kind of say what we mean by a phase transition physically, right? Physics is not math. Keep that in mind, right? So it's not like you're going to go in here and be like, okay, theorem 5.7 proves that at t equals tc, n sub 0 equals 0. That's not physics, right? Physics is saying this is what I mean by a phase transition because I've looked at the natural world. Well, let's see how it looks. So now let's look at this special temperature, the critical temperature, where n sub 0 equals 0. And in that case, basically, we're approximating that all or almost all of the bosons are in excited states. And so we can just sub in T sub c to our formula for the number in excited states, right? And so the total number of bosons is just the total number in excited states at T sub c. And that's this expression, right? So again, almost all particles are in excited states. And now, based on this, the total number of bosons in the system is conserved, right? So this value, this is just a number, 2.612 V times this junk. Whatever this number is the total number of bosons at any temperature, right? don't mean you substitute any temperature in for T sub C. Be careful about thinking what I mean here, right? I've used a specific value of temperature where I think I know something to calculate the total number of bosons in the system. And then whatever number I get by applying this whole formula with T equals T sub C is the number N at any temperature under any conditions. Okay? So that means the number in the ground state is whatever that number was, that number that I got by applying this, minus the temperature-dependent number of excited states. Now, this is only true for T less than or equal to T sub C. Above T sub C, basically, N sub 0 is approximately 0. We don't need to worry about it. All right, so below T sub C, or equal to T sub C, we get the number of atoms in the ground state. Is this the expression for the total number of particles based on the critical temperature, minus the temperature-dependent number of excited states? And so we'll do a little bit of factoring and manipulating, so we factor that out. We multiply and divide by T sub C raised to the 3/2 power. And we get this funny expression that says the number of atoms in the ground state is equal to a number out here times 1 minus T over Tc to the 3/2. So you can see that at T equals Tc, this whole expression is going to go to 0. So the prefactor out there should also look really familiar to you. This front prefactor is just that integral number times volume, but this one should look like de Broglie wavelength or quantum concentration. So this expression is equal to the quantum concentration of the gas evaluated at T sub C. And we know quantum concentration is 1 over de Broglie wavelength quantity cubed, again evaluated at T sub C. And so you can see that the number of ground state atoms per unit volume, where I've just divided out the volume here, which is equal to the number density of atoms in the ground state, is equal to 2.612 times the quantum concentration evaluated at Tc times this temperature-dependent factor that tells us about the transition. So the thing I want to say is, as T goes to 0, the ratio of the number density in the gas to the quantum concentration at Tc is this number 2.612. So that's sort of telling you something about where they get this value of 2.612. But let's look at a plot of this function, which I find really instructive. So this is a plot of n0 over nq as a function of t divided by tc, right? So I'm basically plotting it versus this variable. Above Tc, the number density in the excited state is 0, 0, 0, 0, 0. Sorry, number density in the ground state is 0, right? Again, that's sort of by construction. We're saying if you're at high enough temperature, most of the atoms are in excited states and a negligible fraction are in the ground state. But then you hit this critical temperature, right? And you say, all right, condensation is about to start. And so the number density in the ground state grows, and it grows as this T to the 3/2 power, and it grows and grows and grows and grows. So basically more and more of the gas now is condensing into the ground state, the lowest energy state of the particle in a box for the bosons, right? And as you approach 0 Kelvin, you get that the number density is approaching 2.612, again, in units of this quantum concentration at Tc. So this is a really nice picture, I think, of the physics that we put into this analysis to see what we mean by Bose-Einstein condensation phase transition, right? We mean that there's a particular parameter that is 0, 0, 0, 0, 0, and then suddenly at some special temperature becomes non-zero and grows to dominate the system, right? And so again, you know, what we've done in these slides is all theory, and for many, many decades, from 1924 to 1995, it really wasn't clear, though you could construct that this phase transition is theoretically possible, it really wasn't clear that it would ever be observed in reality, right? So you might be thinking, well, how do we know this happens, right? I mean, we don't. We just built a theory of Bose-Einstein condensation. And until you can make it happen in the lab, you don't know that it's going to happen, right? In some ways, I think what I'm trying to emphasize here is, like, we get to these points where we've made a bunch of approximations, and now we sort of construct this idea of what we mean by phase transition, right? That's our theory. That says this could happen. But then you need to actually go into the lab and try to achieve the right conditions to see if it actually ever will, right? So there is a possibility that before such a thing would ever happen, some other physics would take over, such as liquefaction or solidification or some other phase transition. So again, this really does happen. Basically what you've got here when you're in this regime is you've got a macroscopic number of particles, say maybe a mole of particles, all with one wave function. And this is really interesting and exciting. All right, so I think that's all for chapter 7. And in the next mini lessons for next week, we're actually going to go back for just 2 videos to talk about some thermodynamics from chapter 5. And there are 2 reasons for that. One, the topic is fairly important. It's a topic about mixtures, but also I think it's a really good review of thermodynamics with a very physical feel rather than mathematical formalism like our partial trickery stuff. All right, so we'll talk with you next week.